All right, so I have my rectangular sheet of metal here. This is 8 by 10, and I'm cutting a square out of each corner of length x. So this grand total distance is 10. This little distance is x. This little distance is x. The question is, what does this red distance correspond to? And so in this case, here's my picture. I've cut out the square, right? And so the grand total distance was 10. This is x, this is x. So the question is, how long is this? Because when I fold this up, is it clear? That red is going to be the length of this box. That length of the box is given by this distance from here to here. And what is that? It's the grand total 10. It's not 10. This much is 10. The grand total is 10. We've taken away one of the x's, taken away one of the x's. So this distance, this red distance, is 10, subtract off the 2x. And then in an exactly similar fashion, if this grand total distance on the width is 8, right? Then this blue length is the 8, but we've subtracted off this x, we've subtracted off this x. And when we fold up, this blue length is going to be the width of the box. And so the question is, how long is that blue segment? It's the grand total 8, subtract off one of the x's, subtract off one of the x's. And so this blue distance is 8 minus 2x. Of course, the dimensions of the square are x by x by x. And so this distance is 8 minus 2x, that's the width. The length is the larger, 10 minus 2x. And then the value for x, the depth of the box, or the height, is just x by itself. So when we find the volume of this box, those are the three dimensions we're going to work with. All right, now to have some space to work with, I'm going to have to erase some of this picture. But that's the key notion, is the width is 10 minus 2x. That's found the total, subtract off the squares. The length is 8 minus 2x. That's the total, subtract off the two squares. But then the height is just the width of the square. So I'm going to get rid of this picture. And our task is to find how large should the square be. So we need to find x. All right? Well, what do we need? We need a volume function. And there's only one variable present, so I know it's going to be volume of x. It's length times width times height in any order, so I'm going to write it this way. Minus 2x, length times width times height. Foil that becomes 4x to the second. What do I have here? 4x to the second minus 36x plus 80. And then distribute the x in. That's 4x to the third minus 36x squared plus 80x. All right? So that's the volume function. We need the interval over which that is defined. Well, we talked about that previously. Theoretically, the smallest value for x is 0. The largest value for x is half the shorter original side. So that's 4 in this case. Half of the original shorter side is 8. And so we need to maximize this volume function on that interval. And so now we're off to the races. So we need the derivative to find the critical values. 12x to the second minus 72x plus 80. There are no type 2 critical values. We're only trying to find type 1 critical values. So we set this equal to 0. Now, once you set this equal to 0, now you have an equation. We can divide both sides of the equation by values to eliminate, make these numbers smaller. I'm going to divide everything that appears on both sides of the equation by 4. And if you simplify that out, the derivative simplifies to give us 3x to the second. Divide everything by 4 minus 18x plus 20. And we need to have that set to 0. That implies this is equal to 0. And to solve this, I believe we need to use the quadratic formula. So I'm going to go over here to the side. I'm going to run out of space here, but I'm going to use the quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a. It's the same quadratic formula we all know and love. So it's negative negative 18 plus or minus the square root of negative 18 squared minus 4 times, I believe it's 3 times 20 all over 2a. And if you work that, that becomes 18 plus or minus the square root of 84 over 6, which is 18 plus or minus, this is approximate now, 9.2 all over 6. And if you compute those two values, one of them you get is x is equal to 4.53. The other is x is equal to approximately 1.5. Now these are approximations. These are now approximations, but that's the quadratic formula with these specific numbers. That's very straightforward. Now, here's where this interval starts to earn some of its keep. We notice that 4.53 is outside the interval of interest. And so 4.53 is not used as a critical value because it is not in this interval from 0 to 4. So I'm going to have to erase some of this, but what we need to do now is to evaluate the original function at the values in question. So the original function is here. I need to evaluate the original function at the critical value, 1.5, at 0 and at 4. So here's the original function. I need v of 0. Well, that's not very hard. 0 to the third plus 0 squared plus 0. And that's likely not going to be our maximum. We have volume at 1.5. All right, so we plug 1.5 into this original volume equation. And I'll do that along with you. So I got my little machine here. And I have 4 times 1.5 raised to the third power minus 36 times 1.5 squared plus 80 times 1.5, and the value I have is 52.5. Now that's just one, I haven't checked that, but that's my preliminary value at least. And then the other endpoint, which is 4 times 4 to the third minus 36 times 4 to the second plus 80 times 4. And I think if you work that out, that works out to be 0. And so you choose the larger. All right? So the largest possible volume is 52.5. To satisfy the physics people, we'd say that would be cubic inches. But what are we asked to find? That's why you write this down at the beginning, so you answer what you're asked to find. How large should the square be? The question is not what is the volume, although that might be important. The question is how big does the square need to be? And it's approximate. This is now a decimal approximation.